Okay, so what I want to do today is essentially go through, I just realized something. Give me 1 second. Okay. What I want to do is essentially go through some of the documentation in Hecke and try out the actual functionality that it provides. So we're going to do some simple things like compute class groups and maybe like evaluate the Vey pairing for some elliptic curves defined over number field, finite field. We'll check if we can do like maybe some torsion computations for elliptic curves and some things like this. So I've used Sage before for doing some elliptic curve computations. I'm vaguely familiar with how that might happen, and I know some things that it provides. I think definitely not nearly close to all of what it provides. But I know that, like, for example, you can compute the torsion subgroup, and also you can compute the Vey pairing. And they've got some nice things, like you can actually determine an elliptic curve from like the Cremona classification. And I'd be, I don't know, a little bit surprised if you could do that here, for example. But we're just going to play around today and see what we can do. So I figured we'd start by going through the how-to guides in Hecke. So we'll start with this. So just how do we compute the order in a number field? To create an order, one starts with a number field respectively a defining polynomial. And okay, so functionality for declaring polynomial ring. Looks like we just say qx. This is going to be our polynomial ring. X is going to be name of a variable. So we could do something confusing like this. Right, I forgot to say using Hecke. Where are my fingers at? Okay, so I think we could do something like this, right? And if I do like y squared, prints out that some silly. This is the, I think, one of the most absurd things that you can do in Oscar, Hecke, abstract algebra, and Nemo. And I don't 100% get it, honestly. So we can't do x squared, for example. I think we could have also done something like this. What does this syntax even do? So it's just a symbol. I think in Hecke, this syntax is like some concatenation. Like, it doesn't really make any sense to me. For example, like, let's just try doing something like why was it going back so far? No. All right. I don't know what I was seeing. Huh. Is that a Julia thing, or has my shell always been able to do that? In fact, I kind of want to figure that out. CD? So, like, how come when I say CD, it doesn't do it in shell? So that's Julia specific. It has, like, that feature integrated into it. Okay. So we can do, I'm going to do something more like this. So I'm curious also, how would we pass in, like, something nonsensical maybe? Can I do something like that? And then x squared calls something, and y squared calls something. Is there still an abbreviation though if I do like, so x1, x2. Yeah, that's not so clear to me. The inputs of a lot of this functionality, so I believe that this is a syntax that you can use. I wonder if it's even to some extent the recommended syntax. So we could go to hecke.jl and I don't even think it's going to be in here. I think it's going to be in abstractalgebra.jl. We go to multivariable polynomial functions. So let's start with univariate polynomial functionality. This is just calling a polynomial ring with coefficients, and then this variable name, which defaults to :s, returns a tuple, which is the polynomial ring and the generator. Shorthand version of this construction of this function is provided. Given a base ring R, we can just abbreviate it by like this. I guess the question that I have is like, what does this colon do? A little bit weird. So apparently we can just do that. Wow. And X is just automatic. I think that makes sense because that's like a more natural, in some sense, way of doing it. But in Julia, what's the problem? What's the reason why we have to select some input variable and then get some different output variable? So the way that the types here are implemented, it is in the sense that, okay, there's a parent object, and then elements themselves come as pairs of, well, the element with its designated parent. So whenever you want to create a polynomial ring, you actually have to create an object of type polynomial ring. And then an element, so if you created a polynomial ring R, an element of R would be some pair. It'd be like R comma the element. So if I say, in this case, right, we've used X a lot, but this is a QQ polynomial ring element, which means that it has a parent object, which is a QQ polynomial ring. And that parent is S. Sorry, I meant to type in X there. Univariate polynomial ring in X or QQ. And so we're kind of wondering, there's some things about the just-in-time compiler. So the fact that Julia is shit. I think that would maybe make it have this behavior where it doesn't know actually, I'm not sure. Let's think. So, how we could figure this out is we could ask AI. I think Gemini would actually give us a pretty quick question here. For a pretty quick answer. But we could also look for information in the documentation, which is what we're going to do. So, note, both the generic polynomial type and the abstract type it belongs to are called polyring. These generic polynomials have type generic poly, where T is the type of elements of the coefficient ring. Internally, they consist of a Julia array of coefficients and some additional fields for length and a parent object. Wait, let me read that again. So abstract algebra JL provides a generic polynomial type based on Julia arrays, which is implemented in source generic poly.jl. Doke. So source generic poly.jl. So I imagine we'd be looking for a struct. Poly build. So poly, that's just a vector, and then a parent object. Is that it? So that looks like to me just an implementation of a polynomial. But I don't see any data for the parent or the ring. So I kind of think maybe there's another polyring hom. Universal polynomial ring doesn't look the same in my mind. It doesn't sound the same. Could have been. Yeah, okay, this is not it. Okay, so here's poly.jl, univariate polynomials. Data type and parent object methods. Okay, so here is a universal polynomial ring. I can't even tell if that's non-commutative or commutative. Its own type. Okay. Generic, huh? Okay, so here's the struct that we were looking for. How do you declare a polyring, or what data does that entail? It entails having a base ring, a symbol. So polyring in abstract algebra .jl, the Julie package, it means univariate polynomial ring. So S, a symbol, that I guess is going to be representing the variable, and then is trivial. Okay, that's just a flag, which I guess can speed some things up. And so why would we need this? So let me try to think of some situations. I guess the one thing that I could imagine is something like you define a polynomial ring, you think in your head that that should have coefficients, a field, and then also a generator, some variable. So let's imagine that you just define a ring and then you maybe skip that symbol part, right? Then Okay, if we went to the element struct or constructor, then constructing a polynomial. So struct. So constructing a polynomial, what do we call? So we do generic polyring is going to be the parent with a symbol, which is our variable, and then cached. That's fine. What is a polynomial? It consists of a ring R, an array, which is a vector. That's going to be the coefficients, effectively. And then the variable name you have to confirm. It seems like if I call a polynomial, then that defines a parent also. E.parent is generic polynomial ring TT. R symbol cached. So let's just try calling that. Bad. So we're gonna try calling polynomial of QQ with some array, so like 0, 1, 2. And then variable name is gonna be X. So I don't think I really need to specify that. Great, that did it. And if I do parent of this polynomial, what happens? Univariate polynomial ring in X over QQ. Can I say R is this guy? It's kind of interesting. Okay. So why is it that we return a symbol when you call this? In Sage, for example, you would just say Q is QQ join X or something like this. And then Q would just be that ring. Alright. Let's ask Gemini if there's a reason like you would need to define the variable and then input it, and then something about like if you actually wanted to make a polynomial, then it wouldn't know. That might be something. It might be something like this, right? Like let's say you define a variable and then you try making a polynomial ring, and then you want to do some multiplication. Maybe it's something like that. Maybe you get some polynomial from some polynomial ring, and if I want to do multiplication with the polynomials, then it needs to know what the variable is in order to output that. I can't even imagine that's true. So can you explain why abstract algebra .jl is this syntax for constructing polynomial rings? Why does X appear as an output? Why is X a value? So this is something in particular though, right? Like, if I just do something like, so if I just ignore the variable output, then I'm not going to be able to work with this at all. I have to just call. Somehow I need to export the variable name. But what's the reason for this? This is Julia's syntax for a symbol, so this is the E. Okay. So you're passing the name X to the constructor to tell it what to call. The ring's indeterminate. Yeah, so then why do I need an output if I have the input? Is essentially what I'm wondering. So like if I say Q is QQ, doesn't this already contain the information that Q has as an indeterminate, the value X? So symbol is X. But now if I call it, so let's exit out of this. Clear, and then go to Julia again. I guess this is something that I've always just been confused by. So we'll do Q, pass it X, and then I'll try X squared, and it's undefined, right? So why is that? So I guess I've never understood this one. So we don't define. So if I do something like this, and then I do, okay, well, let's exit again, reset it. I think this is a computer science thing that I'm not getting. So a symbol is just a piece of data, essentially a label. When you execute this, you're passing this label to the constructor. You're telling it build a ring object, and within that object's internal definition called the indeterminate X. The symbol itself has no mathematical meaning and cannot be used for calculations. Sure. The variable. This is a name placeholder in your programming session that refers to an actual object in memory. To write expressions like this, you need a Julia variable X that points to the polynomial object representing the indeterminate. Think of it like building a car. This is the command to the factory to build a car factory. This is the command to the factory to build a, quote, car factory designed to produce a model named Model X. Factory is built, but you don't have any car yet. So let's see. Can you explain the difference between passing X to x and defining the variable x at a low level programming, was. So what actually happens here? So let me think. Here's a breakdown of the difference. High level passing as a symbol. When you execute, QX is QQ, symbol X. You are interacting with a sophisticated abstraction. Right. It's a function call. The syntax is a syntactic sugar for the function call. Specifically, Julia's getIndex function. You are calling a function associated with the QQ object and passing the symbol as an argument. The symbol is data. The symbol is just data. It's a lightweight label that you hand to the function. It has no memory allocated for a polynomial. No associated mathematical properties. It's just a name. It's just an instruction, not an object. Why wouldn't it just create the object also? Inside the getIndex function, a whole sequence of low-level operation happens automatically. Memory allocation. The function allocates memory to the heap on the heap for two distinct objects, the polynomial ring structure Q and the polynomial generator structure X. Initialization. It initializes these memory blocks. For the ring Q, it stores a reference to the base field and sets its indeterminate's name to the string X. Just want to check that technically it's storing as information symbol X, but who knows if that's important. It initializes these memory blocks. For the ring Q, it stores a reference to the base field and sets its indeterminate name to the string X. For the generator X, linking. So for the generator X, it sets its coefficients and stores a pointer back to its parent ring. Return. It bundles the memory addresses of these two newly created objects into a tuple and returns them. Defining a variable at a low level, like in C or what happens under the hood in Julia, is a much more hands-on process. This is kind of what I think I'm interested in. So you're not giving a command, you're performing the steps yourself. Explicit memory management. You would be directly responsible for memory. You would have to know the exact byte, manual procedure, allocate ring. Call a function like malloc to request a block of memory from the operating system for the polynomial ring struct. You receive a raw memory address, a pointer. Populate ring. Manually write data into that memory block. You'd set a field to point to the QQ object. Manually write data into that memory block. You'd set a field to point to the QQ object. Another field to store the character array. X0. Allocate generator. Call malloc again to get another block of memory for the polynomial generator object. Populate generator. Manually write data into the generator's memory block. You'd set its degree, allocate space for its coefficients, store this, and critically store the memory address of the ring you created in step 1. Yeah, I want to know why you want the difference between these two, though. So this is what I want to know. Okay, so I think some of this is that I don't have a good understanding of low-level programming. So, there's one memory address. Okay, so let me just abstract it a little bit. So there's one memory block which stores information of the following. So one, when I do this construction, it performs this it blocks out a space in memory which has options to fill it with the following. One is a pointer that goes to wherever QQ is. So it's just here, right? QQ polynomial ring. I imagine that this is like somewhere it must be pointing to QQ. And then the second one is it points to the name, a symbol X. And so now I'm kind of getting that, like, when I define a new variable, it creates a totally different memory block, which is going to be the actual polynomial X that we'll construct. And now I'm just wondering, I guess as a polynomial ring, what you don't want is that you have two pointers. One of them points to a variable X. And then you'd probably still have to do the other thing. Like if you want to construct a polynomial in X, then you have to specify some other block of memory, and then you point to the variable X again. Yeah, that's kind of understandable. So in comparison, okay, if we were making a polynomial ring and we had a pointer to like the QQ coefficients and then a pointer to some variable X, and then that was the variable that we were going to use, assuming it was mutable, I could see that being bad, right? Because then we'd have a polynomial and some changing variable. I guess what I'm kind of thinking is just that so when I do an operation like create a polynomial, like this, right? Then and what's going on here? Like, what is this thing representing? Is it just representing so at some point it prints, and then like this X here, is it just pointing to some X in memory which is stored in the polynomial ring? And so like doing, for example, this operation does some multiplication, you get some array. As you go up indexing the array, it just changes what the pointer value should be, and then you also have like an indexing value. So the pointer always goes to X, I guess, and then you just keep track of indexing for which step you are in the array that you get from the polynomial. Kind of buy that. So let me think about this. So if I have Q is QQ calling this, then I have to define X in order to actually manipulate it. Okay, so let me get this straight. We get a block of memory allocated, which points to coefficient ring and a symbol. I call x equals gens q. And an array is generated. A block of memory is allocated, which contains an array. And a reference to Q. When I perform x squared, manipulations produce array 0, 0, 1, and Hecke / Julia prints x squared, where x is pointing to the symbol stored in Q. Let's do x squared plus 1. Is this kind of right? Okay, when this is executed, a block of memory is allocated for the ring object. This object acts as a rulebook for all polynomials that belong to it. It contains 2 pieces of information, coefficient ring, and the name of the indeterminate. Okay, when I call this, this creates another block of memory for the generated polynomial object, which you assign to the variable x. This object represents the simplest possible polynomial, and its memory block contains its coefficient representation, which for x is the array 0, 1. Okay, and then a reference pointing back to its parent Q. Great. And then printing this thing. So this is the most insightful part. When you compute this, the library's overloaded exponentiation operator and plus operators are called. They look at the object x, see its parent Q, and use the rules defined in Q to perform the math. This calculation creates a brand new polynomial object in memory. Yeah, okay. Believe that. This new object contains the resulting coefficient array, and then a reference to the parent ring, also Q. Printing. So when you ask Julia to print this new object, the printing function is called. It does not point to the symbol stored in Q. Instead, it performs a clever reconstruction. It looks at the coefficient array, looks at the object's parent ring Q. It asks Q, what is the name of your variable? And Q replies to X, which is stored in the struct Q, which is, I imagine, a pointer to the name X or something like this. I guess I don't know what pointer means, but it references X, sure. Print function then iterates through the coefficient array, combining the coefficients with the variable name and the appropriate powers to build the human readable string. So the X in the final output is dynamically generated for display by looking up the name stored in the parent ring. This is how different rings can have different variable names, and this is keeps everything straight. Okay, then can you confirm? Okay, can you tell me what a pointer is? A pointer, I'm pretty sure, is just some pointer. Like, it's just some reference that tells you exactly where some memory block is. So I don't think this is the best thing. So, so to clarify, in 2, there is no pointer to X. Can you explain this? And explain why you would not use pointer here. That's correct. To be precise, in step 2, the generator object X does not have a direct pointer reference to the name X. It only has a reference to its parent ring, Q. Design choice is crucial for efficiency. Imagine you have a very complex polynomial, something to the 100. This P is also an object, just like the simple generator X. Right. If every polynomial object had to store its own copy of the variable named x, no, I don't imagine that the polynomial is storing the variable. It's just q that stores the variable. That's what I'm saying, though. I get that. Why pointer isn't the best word here. Reference versus pointer. You're right to question the terminology. While pointer gets the general idea across, the more accurate term in high-level languages like Julia is reference. A pointer is a low-level concept, most famously from languages like C, C++. It's a variable that stores a raw memory address. Programmers must manually manage this memory, which is powerful but can lead to errors like memory leaks or crashes if not handled perfectly. A reference is a high-level, safer abstraction. It's a variable that refers to another object. Like a pointer, it tells the system where an object is located, but you don't interact with the memory address directly. The language's runtime and garbage collector manage the underlying memory for you automatically. The language's runtime and garbage collector manage the underlying memory for you automatically, preventing common pointer-related bugs. So when we say the polynomial x has a reference to the ring q, we mean it holds a safe managed link to the q object. Using pointer isn't strictly wrong in a conceptual sense, but reference is more precise. Okay, then what we wanted to ask after this was, pointer is a low-level concept, most commonly used from languages like C, C++. It's a variable that stores a raw memory address. Oh yeah, what's a variable? Is there definition of a variable here? It's a variable that stores Okay, there's a precise computer science definition. Great. In programming, a variable is a symbolic name and identifier associated with a storage location in memory, which holds a value or a reference to another object. Okay, so a variable is a symbolic name associated with a storage location. Name. This is human readable code. Storage location. Memory. Behind the scenes, the system reserves a specific slot in the computer's memory, RAM, for the variable. This location is the actual place where the information is kept. Value or reference. Value types. For simple primitive data types like integers, floating point numbers, or booleans, the variable's memory location we skipped the definition, right? You're already using variable. For simple primitive data types, variable's memory location often stores the actual data directly. Variable's memory location often stores it. If a variable n is assigned the integer 5, the binary pattern for 5 is placed directly into n's memory slot. Reference types. Complex data structures like our polynomial objects, arrays, or dictionaries, storing the entire object directly in the variable slot would be inefficient. Instead, the object is created in a larger, more flexible area of memory called the heap. And the variable's memory slot stores a reference, essentially a managed memory address that points to where the actual object is. I think that's just because sometimes you don't need to actually go through. I mean, I think you can manipulate the pointers without actually ever manipulating the object is the crucial part there. Why would you need to do that? I don't know. When we said it's a variable that stores a reference, we were being precise. In our example, x gen q is, the steps are: a polynomial object is created in memory. A variable named x is created. The memory slot for x doesn't hold the entire polynomial, it holds a reference pointing to that polynomial object. So the variable isn't the object itself, it's the named handle you use to access the object. It's just the name. Is the variable just the name? Is a variable A symbolic, a reference. So is this a good definition? Variable is the combination of both a name and a location in memory that is referred to by that name. How would you change the definition? And actually, just what's the Wikipedia definition? Okay. In computer programming, a variable is an abstract storage location paired with an associated symbolic name, which contains some known or unknown quantity of data or object referred to as a value. Which contains some unknown quantity of data or object referred to as a value. Okay, which is like, what, a collection of binaries, I guess, or a collection of bits? Or in simpler terms, a variable is a named container for a particular set of bits of a type of data. Okay. I think we can go on from here. Hmm. I guess that is something that I didn't think about either. Is like when you specify a variable in the terminal, like if I said like I don't know, foo equals 5, right? Okay. Then and there's a few things that I'm doing, I guess, is that I have to tell the computer to remember foo. And then the computer also has to remember that foo points to 5. So then if it sees foo again, it knows that it should go call 5. But how does it remember 5? How does it remember that foo is there? Okay, so here's another question. So let's say fine, foo equals 5. We write foo equals 5 in the Julia REPL. Then the computer remembers needs to remember both that foo is defined and that foo points the integer 5. How does the computer remember that foo is defined? I guess it doesn't need to. Because technically what you could do is you could just like, I mean, it doesn't need to. It could just go through and say like, is foo stored in this list? And if foo's stored in this list, then it's pointing to this memory thing. It actually doesn't need to. So, does the computer store the information that foo is defined, or is it searched for each time foo is called? I guess I guess there's probably different answers to this question for different things. Like in Julia, maybe it's just cached in each session. It's not like a lot of information. Maybe in other times it's actually searched though. I mean, definitely you can imagine like in a bare bones computer where you've got like 7 logic gates, like maybe 700 logic gates strung together in some basic functions. Maybe you actually would need to search each time, or yeah, so it's stored in a dictionary like data structure called a symbol table. That's kind of a new thing I haven't seen before. This is specific for Julia, maybe. Think of the Julia REPL's current session as having a dedicated high-speed dictionary. This is its symbol table. The variable's name and value, whatever it refers to. The object the variable refers to. This structure is typically implemented as a hash map, which makes sense for a simple REPL. Yeah, so then let's ask this. If instead of a Julia REPL, we had used a bash shell, born again shell, would the answer stay the same? I never thought that I would be sitting here parsing questions back and forth between Gemini, just trying to learn something. But it's kind of neat. And also, I've totally gone off the rails with what I was planning on doing here. So the Born-again shell also stores its variables in memory for fast lookups and does not search for them from scratch each time you call them. The high-level principle of using an in-memory table for efficiency is standard design for interpreters and shells. However, there are some crucial differences in what is stored and how it's treated. Bash adds an entry to its internal list of shell variables. The key is the name foo and the value is 5. This information is now stored in the shell's memory for the duration of the session. When bash encounters the variable foo, it performs a fast lookup in its internal variable table to find the value associated with foo. It does not reread configuration files or perform a slow search. While the storage mechanism is similar, what's being stored is fundamentally different, which is a major distinction between programming language environment and shell. One, everything is a string. This is the most important difference. In bash, variables hold strings of characters. When you type foo equals 5, bash does not store the number 5, it stores the character 5 as a string. If you want to perform arithmetic, you must use special syntax, like parenthesis, to tell bash to interpret the string as a number for that specific operation. In contrast, when you type foo equals 5 in Julia, it stores a true 64-bit integer object. Julia's type system is rich and tracks the type of every value. What low-level languages are used to write Julia? To write the Julia language. I think there's a hierarchy. I know that Julia goes down to LLVM, so maybe that doesn't count as being written. Maybe Julia is its own language. Maybe this is a stupid question. Maybe not. Okay, Julia is written in a combination of C and C++ and a dialect of Scheme called Femtolisp. A large portion of its standard library is also written in Julia itself. The core of Julia, including its runtime system, is built with C and C++. These languages are used for the most performance-critical components where direct memory management and raw speed are essential. This includes the Julia runtime, which manages the execution of Julia code, the garbage collector, which handles automatic memory management, the interface to the LLVM JIT compiler. LLVM is a powerful compiler infrastructure, also written in C++, that Julia uses to generate highly optimized machine code. Many of the fundamental numerical libraries are C or Fortran libraries that Julia calls into using a C interface. Julia's parser, part of the compiler that reads your code and understands its structure. Let me actually think about what a parser is. I tried learning this the other day, so I'm gonna look it up. Because there's parsers, there's interpreters, there's compilers, all in the process of changing your code into binary. And there's different for like interpreted languages and compiled languages. So parsing is a process of analyzing a string of symbols, either in natural language, computer language, or data structures, conforming to the rules of formal grammar by breaking it into parts. The term parsing comes from the term has slightly different meanings in different branches of linguistics and computer science. So parsers, computer science. Okay. In some machine syntactic parsing, computational linguistics. Is that what I want? I want to see this. A parser is a software component that takes input data, typically text, and builds a data structure, often some kind of parse tree. Parse tree is an ordered rooted tree that represents the syntactic structure of a string according to some context-free grammar. It's an ordered rooted tree that represents the syntactic structure of a string according to some context-free grammar. Okay, often some kind of parse tree or other hierarchical structure, giving a structural representation of the input while checking for correct syntax. The parsing may be preceded or followed by other steps, or these may be combined into a single step. The parser is often preceded by a separate lexical analyzer, which creates tokens from the sequence of input characters. Alternatively, these can be combined in scannerless parsing. Parsers may be programmed by hand. Okay, so what I'm imagining for this is like, you write a bunch of code, you have a bunch of names for shit, like function, right? That's a keyword in, for example, Julia. Then what a parser does is it takes function. When it goes through your code, it takes the word function and replaces it with whatever that's supposed to refer to, is what I think. And then I guess it builds this data structure, which is the parse tree, which is like, it goes out, maybe takes away each of these parts and replaces them with like a different node. And then how does it have the tree structure? So what would each node actually be? I want to say that the parentheses would make somehow, like if you actually went out, I kind of want to say that the parentheses would be what dictates the tree structure. So I kind of get how this could happen in my mind. So like, for example, function and end, that's like a environment or some parentheses. And then there's stuff that happens inside of this, and so if I was just thinking about function and end, for example, I could have like as a top node, this is kind of that whole environment, function and end. Let me just do something simple, like function inputs x and it outputs x plus 1, right? So then let's take no, there's syntax that I think is hard in here. I guess I don't know how to get it inside or outside. Like x needs to be called, plus needs to be called, and 1 needs to be kind of referenced. And you need to do x plus 1, and that all happens inside the function. And so should you have as a node like an x, a plus, and a 1, and then these all point to the function? Or should you have something like x should be defined, and then and then 1, so it's just like a line as a tree. I'm not sure. I don't know if I really care either. So here's a way to get a sentence into this. So John hit the ball. So we've got something like this. And that's essentially what you want to do. But I guess separating it out into things like, what are they separating out into? Like noun. Okay, so sentence, noun, verb, phrase. Okay, noun, phrase, verb, determiner, noun. So there's different layers for things probably like maybe variables, functions. Maybe they have things like function phrase and variable phrase. Kind of not sure, but okay. The input to a parser is typically text written in some computer languages, but may also be text in a natural language or less structural. Parsers range from very simple functions such as scanf to complex programs such as the front end of C++ compiler, the HTML parser of a web browser. An important class of simple parsing is done using regular expressions, in which a group of regular expressions defines a regular language, and a regular expression engine automatically generating a parser for that language, allowing pattern matching and extraction of text. Group of regulars defines a regular expression engine automatically generating a parser for that language. It's kind of a shitty sentence. A group of regular expressions defines a regular language and a regular expression engine that automatically generates a parser for that language, or which is automatically generating a parser for that language, allowing pattern matching and extraction of text. In other contexts, regular expressions are instead used prior to parsing as the lexing step whose output is then used by the parser. Okay, let's try looking at this. Fuck it. Okay, I think I've gone deep enough down the rabbit hole where I'm cool with going back. I was kind of thinking after reading some of this that maybe there are like critical algorithms that should be written in a very low level language, but it's hard to do that when your major structs are in higher level places. I guess not impossible sometimes, but for example, msolve is this interface which does Grosvenor basis over finite fields, and it's written in C, but it's not clear right to me because Hecke or Oscar, they don't have the same type system as Julia, so their types for things like finite fields, if they wanted to interact with msolve, which they do, because they have an interface to it, they have to somehow pass that information of like which field they're working in, for example, to msolve so that you can do some Grosvenor basis calculation. That's kind of interesting. There's a lot of computer science that goes into it. Okay, let's just move on. So we're going back to this. So I pretty much... Okay, so starting out, we're just trying to figure out, like, what... Well, we didn't even make it past the first line. Starting out, we got super distracted by just what is this line doing, and I didn't understand why you need to define x as well as pass it in. But now I know that I think what this is doing is saying, like, okay, we're gonna have a variable x, we're gonna create a ring object which points to both QQ and x, and then you can take your ring and then also create a polynomial x if you want to manipulate it. Okay, then, so let's ignore that and let's try to do a number field. So we'll take, okay, so this is interesting too. So we're gonna create a number field. Let's pick x to the fifth minus x plus 1. And do I need the x? Or does it just automatically generate the polynomial? Does it parse the polynomial that I've just typed in into something understandable, or do I need to have the defining? Usually to create an order one starts the number field respectively defining a polynomial. So this is going to determine for me, I think, I don't really see why it wouldn't return just an actual object. Great. I mean, you don't know that this is a symbol, right? So it wants an actual polynomial. But it's like, I think it should be possible to understand that, right? If you have a character passed in here, then okay, I get it. I get it's probably a lot of work. So let's define a polynomial ring like this, and then define number field, and we'll do the one that I was trying to do. Okay, so this is a number field of degree 5 over QQ, and A is just A. I mean, it should be a root, so it is. Okay, how is that done? It could just be performing quotient arithmetic, right? So, like, there's nothing really unique here, I feel like. How do I get one where I think that it should return to me something completely different? Okay, so that's not too surprising. This is just giving me the quotient ring of the polynomial ring that I generated modulo this. So what does that do, and what is going on when I define these elements? And is passing a symbol the only way that I can do this? So let me think. Oh, it's just division, right? What you do is you take, like, you just take x to the 5th minus x plus 1, do the long division algorithm, whatever I'm typing in. So, like, minus a to the 6th minus a plus 1. I divide it by this polynomial, but substitute it in with the symbol a. And then I reduce. So I wonder if that is in the code to some extent. So let's go to number fields. Number field operations. These are abs. Okay, is it just number field? Simple number field. Field pure and Kummer extensions. So is radical extension, is Kummer extension, basis, discriminant, absolute discriminant, is subfield, linear disjointness, primitive element. Simple number field, include simple number field fields, simple number field subfields. What we want though is something like this. Okay, so the string S for us A is used only for printing the primitive element B. Right. Function doc stub nf end. Why is this in the doc? Doc, you dummy. What is this about? I thought that I was going to see to work around a bug in the build documentation. Oh, is that a recent thing? Four days ago? I guess it was. So let's just go into here. Huh. I understand that. So this is what I thought. What does this mean though? So what is the doc? What the fuck is this doc about? So let's just leave that there, and then Look for... I guess I just don't understand. Of course, this code is a clever workaround in Julia for applying the same documentation string to multiple different versions of a function name number field. Okay, so it's just somewhere else, huh? The documentation cloning macro. This inner part retrieves the documentation string that was attached to our placeholder function. This outer part takes the string retrieved from the inner part and applies it as the documentation for the number field method. That follows. Okay. Alrighty. So let's see. It's interesting that there's a quadratic field definition also, other than just a number field definition. Can't imagine that it would, you know, be different. Okay, maybe I can't imagine that it's different. Because you can reduce some of the computation, I guess. Oh no, this is just saying if the number of bits gets too big, then the square root function is not precise anymore. Okay, this is a long file. It's fine if there's a number field definition. Okay, so you can define a number field from a Euclidean ring residue ring. You can define it from a polynomial ring with a variable name. A polynomial ring LM. We took a QQ field LM. So that should also be somewhere around. Or we could try something like 1/2. And still works. These are all the field constructions here. And I'm wondering if I want to know, I think there is a there's a way to do this. It's just an @which macro. Number field QQ poly ring LM S is a union of character abstract string a symbol. Catch check. This is a Nemo. nemo.jl. So we would go to Antic and number field LM. Get it right. Antic types, absolutely simple number field. This is a basic type for absolute extensions. Operation is usually called by calling number field at ref. See also. So we get a QQ polynomial ring, symbol, catch. And then there's also probably so this one says at Nemo in NFLM 1096. Jesus Christ. Okay. Great. Let's carry on. So, I think a goal, because I'm not going to be up for too much longer. I think a good goal for the end of the night would be something like trying to compute the class group of this number field, and then trying also maybe to define an elliptic curve over this number field. So let's just clear. So if we want to define a number field, we need a polynomial, for example, but we could also do this in other ways. So we could do R as a polynomial ring. Over the integers, and then we could say KA is a number field for this polynomial, and this is also an apps simple number field. Okay, great. I guess if I do like a squared, 8 to the 6, 8 to the 7. The variable that it displays in is lowercase a. That's fine. So we can define an order. That's cool. We can get a maximal order. I'm not sure how this would be defined. If you have an integral polynomial, a monic integral polynomial, like we do, then we can get an order by generated by just the root. That's fine. A maximal order. How would we produce a maximal order? I'll have to think about that, just to think if it's a number theory algorithm. We do have, when we get just any order, we get some, like I wonder, just called L. happens to be the integral order. So we get some lattice inside of this number field, which has the same rank. So if we tensored it with k, this lattice, then we would actually get k. If we tensor this with q, then we would get k. So it's finite dimensional. So it's a finite rank Z module, which is a ring, and when you extend scalars, gives you the whole field. Although here, it ended up that we could get more. So let's think about that for a moment. I don't know how you do that. So how would you algorithm for determining maximal? In number field. In ring. So there is an algorithm for number fields called the Buchmann-Lenstra algorithm. Just so you can see what I'm saying, right? This is Will Stein's website, where he's explaining how to find a maximal order. But I actually can't read the website, so we'll try going to just Chrome. And pasting this in there. It didn't fix anything, so won't show you that. Man, that was probably a good reference too. And it seemed like it didn't need to be a number field. So in this paper, we studied the algorithmic problem of finding the ring of integers of a given algebraic number field. In practice, this problem is often considered well solved, but theoretical results indicate that it is intractable for number fields that are defined by coefficients with very large coefficients. A subring of the number field that one may view as the best guess one has for the ring of integers. This best guess is probably often correct. Our main concern is what can be proved about the subring. We show that it is practically a transparent local structure, which is reminiscent of the structure of tamely ramified extensions of local fields. A major portion of the paper is devoted to the study of rings that are tame or more general sense. As a byproduct, we prove complexity results that elaborate upon a result of Chistov. The Chistov. Paper also includes a section that discusses polynomial time algorithms related to finally generated within groups. Undo that shit, man. Okay. Algorithm. Factoring a finite separable algebra. Algorithm. Factoring a general prime ideal. In a number field. God, I wonder if homepage is still updated. Okay. Right, so we can compute a maximal order. If we wanted, we could define an order ourselves. Could I mess that up, though? Oh, it produces the smallest order that contains a certain amount of elements. So I could say this is going to be order from K with elements just A and 2A. Sorry, 2A and 3A squared. So it seems like it shouldn't give me the same thing, right? Needs to be closed under multiplication. And if I have A, then I get everything. I get that. Okay, that didn't give me everything. If I start with 2A, though, it's not obvious that you'll get everything, but maybe the 3A squared with A actually helps a little bit, because you can use like some GCD calculation or something. Right. Let's turn to top. How do I... Is my browser just totally fucked? How do we decompose a prime in the ring of integers? That's totally possible. How do we test if an ideal is principal? How do we construct a residue field? I wanted to compute a class group. And there is an example of that somewhere. So all we have to do is just take the maximal order. Is that obvious that that's going to be the ring of integers? It might be. It might be. That might just be some theorem. It's been a while since I've thought about this. So the definition of order is sometimes somewhat context dependent. This symbol's definition of algebraic number field, where R is a subring that is finally generated Z module, which contains a rational basis. That's kind of similar to the definition of an order in a division ring, except you kind of replace Q with your or a maximal order in a central symbol algebra. You kind of replace Q with a base central symbol algebra, and then you replace F with some extension, some central symbol algebra containing. Wait, is that true? Yeah, the example that I would always think of is something like this. Okay, I have a matrix ring Mn of Q, and a maximal order should be like Mn of Z. And what it should be, so what is the context here? We have Z as like a DVR. It's not a DVR, fucking a Dedekind domain. And then this is it. So okay, so if I take I guess I can do this for any domain. So if I have a domain, and if I have a central symbol, if I have an Asimai algebra over that domain, then I get some central symbol algebra on the generic fibers, so localizing at 0. And a maximal order inside that guy should be a maximal order with respect to the domain, I guess. Should be an algebra, which is so it's a ring. Should be an algebra under the domain, and it should have the property that when you tensor it with the generic fiber, so when you localize at 0, then you get the whole central symbol algebra of the generic fiber. And then maximal would mean something like, you also want it to be kind of like a finite rank module under the domain, though. And then maximal would mean like it's the largest such one. Okay, I don't ever want to think about this to some extent. Compact open subring of a local field. R is an integral domain with factor field K, and R order is finite dimensional K algebra A. An R order in a finite dimensional K algebra A is a subring of that algebra, which is a full R lattice, i.e. it's finite module with the property that it tensors to K. That's kind of what I was just saying with the division algebra. I just could have, I guess, generalized it to an arbitrary algebra. When A is not a commutative ring, the ideal of order is still important. Phenomena are different. If A is an integral element over R, then the polynomial ring R join A is in R order in the algebra. That's true, and actually this is something from T. McDonald, right? Which is that if R join A is finite as an R module, then A is integral. And so if we think about maximal order, we're taking kind of all the union of all such of these, because whenever we add an element to the order, we also add this kind of polynomial ring, and so that is the union of all integral elements. Okay, so maximal order is the integral closure, I guess. So if R is an integral domain and L is a finite several extension of K, then integral closure S of R and L is an R order in L. Right. Okay, so this actually is true. God damn. Alright, and so now we can just define, don't really need the map, so we can ignore it and see what happens if we just draw a right class group of our maximal order, which is L. So before this computes, let me try to guess what it should be, if I can remember. I don't know. Z mod 1? Okay, I should be able to say what's the order of C, but that kind of checks out. So what can I call for C? That's a lot of stuff. It's kind of crazy, actually, you know, think about it. Okay, maybe that was my bad. So let's say instead of calling C like this, I call C and then I just forget the map like that. Okay, now if I dump C, what happens? F is really the thing that's taking up a lot of information here. And why does it need to take up information? What map do I think I get out of this? Kind of couldn't tell you. You get a map class group. Map class group goes from finally generated abelian group to Hecke absolute number field order ideal set. So is that just giving me representatives? It's kind of impressive, although very extra. So, well, you do want to know what a representative is, but God, it must be challenging to do that to some extent. So, okay, great. Exponent's 1, that means that's trivial. So that means that this is, so x to the 5th minus x plus 1. Let's just look up this U of D. So, it's kind of not what I want. Okay, that was the craziest shit I've ever seen in my life. I thought that that would just somehow... My bad. I thought that would somehow just incorporate into Gemini. And then I think that it is going to give me a more precise reference than what I was finding on a Google search. This polynomial is a pretty well-known polynomial. Like, if I just look this polynomial up, I think that I should be able to find something. Why is this polynomial well-known? I think it's the general form of a quintic. And this is kind of a fun thing, is that it has no exact root. So there is a way to explain this root. Like, there's no algebraic exact form. This is one of the polynomials where the roots aren't solvable, but it is solvable by transcendental functions. So, yeah, it might be possible that we can find this. Oh shit, wait. Yeah, maybe I had a minus and a plus switched around, but kind of thought this one would work too. God, I want to see solving quintic equations with transcendental functions. Oh yeah, it's ring radicals is what the name is. Okay, so in algebra, the ring radical or ultra radical of real number a is the unique real root of the polynomial blah blah blah. I guess ours would be if we used a as -1 and then we negated the whole thing. That doesn't really work. Doesn't really work. All right, whatever. So you can do this trick with the Minkowski bound here. Okay. And then just check explicitly for primes that have norm 2 and 3. I wonder if that's the algorithm that's used to compute this, where basically what you do is you take the Minkowski bound for the number field, and then you decompose each of the primes that are less than that bound, and then you're good. Okay, I think I'm probably gonna head off to bed also. So didn't get very far in terms of the main goal today, which was learning more about Hecke's functionality. Literally the only thing that we did was computed a class group for some number field, and then we spent like most of the time stuck on why, for computer science reasons, do we need to define a variable even though we've already passed in the variable into the ring constructor. So anywho, yeah, I think that's it for today. I was thinking more about this variable thing and thinking about the scope of the function itself that does the construction. Why you can't like call the variable inside the local scope of the function and then have it available outside that scope. But that's definitely a Julia thing. And I'm gonna go to sleep because it's getting pretty late. And thanks for joining me again, I guess.